In this exercise, we want to determine the initial rate of a reaction. So we have an enzyme reaction where we have a substrate which is converted by an enzyme into a product. And conveniently, the substrate has an absorbance that we can measure. It has an extinction coefficient of 3322 per molar and centimeter. So we can nicely follow the disappearance and the conversion of the substrate into the product. The product does not show any absorbance, so we won't see the generation of this product. We just see the decline in the substrate. And here we've got our measurements. So we measure in a spectrophotometer in a cuvette with a path length of 1 centimeter. We measure this disappearance, and we measure every 10 seconds. We measure the disappearance of the substrate by just simply looking at the absorbance. So first of all, we need to check whether this is actually a linear relationship, whether this gives us a straight line. So we can do that by simply plotting these data. So we plot time versus the absorbance. So I highlight the cells by pressing the Control and the left mouse button, and then we go to Insert here, and we go to Charts and draw a simple scatter plot. So this here is our scatter plot. Of course, we would need to label the axes if that was an assignment. So we could, for example, say we have on the axis of on the x-axis we have here the time, and that would be in seconds, and on the y-axis we have the absorbance. And that gives us this straight line. We can check whether this is indeed a true straight line. So by right mouse click on one of these dots, we can add a trend line to that. So here we can look at the trend line, and the line of best fit is indeed a very good and straight line. So it looks like we have a very linear relationship. We can even display the equation on the chart here. We find that for the Pearson's correlation coefficient we get a value of 1, which indicates it's almost a perfect fit here, and that looks very convincing. And we also get our gradient here. Because it is negative, we have a negative gradient. So our gradient, which is the rate of the reaction, and we can write that down. Rate equals 0.0072. I quickly show you how we can also do that without this plot here. There is a very convenient function in Excel. So we start typing equals slope, and that is a built-in function of Excel which will calculate the gradient. So we have to do the y values, so our absorbance is first, highlighted by the left mouse click, comma, the x values, in this case the time, close the bracket, and we get a rate of negative 0.00722. So this slope method, the calculated method, is a little bit more accurate than the one here on the graph. So that would be our rate, and of course the unit for this would be per second. Now, of course, we can calculate that per minute. So we can calculate the rate per minute. And that would be just simply by taking 0.00722 times 60. So that would give us the rate. And if we put that into a calculator, we would get the rate of 0.433 per minute. And that would be absorbance units, if we like. Now we can calculate we can convert that into concentration change. We know from the Beer-Lambert law that an absorbance is given as the concentration times the extinction coefficient epsilon times the path length, and I write this as L for centimeter. We can quickly rearrange this equation to get the concentration. So we would get concentration equals the absorbance divided by the extinction coefficient and the path length. So that's what we've got here. And instead of the absorbance, we can put in here the change in the concentration would be the change in the absorbance. So our change in the concentration would be our change, and I symbolize that with this delta, A divided by epsilon times L. All we need to do is put in our numbers. So we have just calculated the change in absorbance. That was 0.4332 per minute divided by epsilon. That was 3,222 molar to the minus 1 centimeter minus 1 times 1 centimeter. We see the centimeter units cancels out. So what we have got left is 0.4332 divided by 3,322 molar to the minus 1 minute. And if we put that into a calculator, we get roughly 1.3 times 10 to the minus 4, and the unit here would be molar per minute. So that is how we can very nicely calculate the initial rate. The units are correct because we see a change in concentration per time, and we have got the conversion correct. So I hope this makes sense, and thank you very much for watching.